Alright, welcome to another AQA AS Chemistry video. So this will be a two-part video. We're starting organic analysis, and this is a two-part video for reactions. In this video we're going to go through testing alcohols, the problems with certain tests, overcoming those problems, we're going to be going through aldehydes and ketones in this first section, and specific tests to get to truly identify certain chemicals. So when we're testing alcohols, we can test alcohols to decide whether they're primary, secondary, or tertiary. The test, we must warm the alcohol and then add acidified potassium dichromate, so you have your own apparatus for that. So both primary and secondary alcohols will form a green precipitate, and that's the acidified potassium dichromate that's being reduced. But with a tertiary alcohol, there'll be no observable reaction. The problem with this is that with this reaction, so this is good for identifying primary and secondary alcohols, but the problem with this is that it provides the same result, or it gives the same result for primary and secondary alcohols. So it's hard to decipher between. For this specific reaction, when you're using acidified potassium dichromate, it's hard to determine whether or not it's a primary or a secondary alcohol, since they give you the same end product or the same observable reaction. A rough way of differentiating between the two is that if you did this method, generally is that primary alcohols will react faster, i.e. they will reduce the potassium dichromate faster compared to secondary alcohols. What I mean by that is that if you're observing this reaction, the green precipitate will form first with the primary alcohol compared to the secondary alcohol. You'll see it, but this is quite unreliable. I wouldn't trust this method, but if you really want to know that method and you just see a difference, then you know the reason why. We can overcome the problem, so a better way to differentiate is by testing the products of the first test. So in the first test, the acidified potassium dichromate 5 oxidizes. So primary alcohols form aldehydes, and secondary alcohols oxidize to ketones. And we can carry out aldehyde/ketone tests that I've done before to determine which alcohol was initially present. So the aldehyde/ketone test uses either Fehling solution or Tollens reagent, and I've already covered that in my previous video. Aldehydes or ketones. So we can determine whether a chemical is an aldehyde or ketone through two possible tests. So obviously, I have two chemicals here. I want you to identify the names of the two compounds that I have here, and I want you to name which one is the aldehyde and the ketone. Very simple one, but I'll give you like a couple seconds to do that, and then yeah, that's it. So that should be enough. I was going to say pause the video, but I don't think you really need to pause the video to answer this question. But this is propanol. And this is propanone. I should probably get a harder example, but I can do that later. Aldehydes and ketones. So aldehydes and ketones have very similar functional groups, and so are, as I said, they are very similar. As I said in my previous video, again, you can watch that. I probably will put a link in the description to that previous video, but it's literally the last video that I made on the channel. So aldehydes and ketones have very similar functional groups and are hard to tell apart. The one feature that they have that's different is their oxidizing ability, and so oxidizing agents can be used to identify which is present. So when we're talking about oxidizing ability here, there's different levels, and of course if I was to go for the second, if it goes to go further, for example, for an aldehyde, let's pick the example that I had before, which is propanol. And different levels of alcohol have different levels of oxidizing ability. Aldehydes can be oxidized further twice to carboxylic acids, and this is due to the CH bond that can be broken down for oxidation. So ketones can be further oxidized, but only so ketones can't be further oxidized, so they can only be oxidized once. And as I said before, you won't be breaking the carbon-carbon covalent bonds. The Fehling solution. So our first test is Fehling solution. A lot of the content that I have here is from previous video, but this is just a video on the test that you write down in the exam, because this always comes up in the exam. They always ask you, not specifically, they'll never say, what's this reaction to this? They'll say, so a student has compound V, compound X, and they want to prove that it's this, or they want to identify it, and they're giving you these reactions. They know it's an alcohol, so and so. So this, when you're actually writing your exams, you need to say the reagents that you're using and the color changes. So one of them, as I said before, is the Fehling solution. And our first test is with Fehling solution. It contains a deep blue Cu2+, and it's so it contains CO2+, and it's a deep blue color. Sorry. When you add an aldehyde, the C2+ oxidizes. When you add an aldehyde, the C2+ oxidizes the aldehyde, and it is reduced to Cu+, causing a color change from a deep blue to form a brick red precipitate. And that's most important here. You have to say precipitate, not just a brick red solution. It actually forms brick red precipitate. And that brick red precipitate is just the Cu+ ions here. But with a ketone, there's no color change because it can't be oxidized any further. As I said before, you have to break these carbon-carbon bonds, and that doesn't happen. You can't do that. With Torrance reagent contains the diamine silver 1+ ion, or AgNH3 2+. You don't need to know about. You need to know of this structure, but in year 2 you'll learn more about these type of transition metals. But you need to know of this like the formula for it, and it's a positive charge. The reason why is because this is a clear solution when obviously as itself is a clear solution, but because it's a clear solution. However, when the reagent oxidizes an aldehyde, the silver or the Ag+ gets reduced to form Ag solid. And then it'll form a silver mirror. So it's like this. So this reagent doesn't oxidize. It oxidizes the aldehydes, but it won't do anything to a ketone. And as I said before, these questions usually come up in 6-mark questions. But yeah, with an aldehyde, the Ag+ will oxidize an aldehyde, and it will reduce the Ag+ ion in this transition metal complex, and it's reduced to solid silver, and this is said to form a silver mirror on the surface of the test tube. Make sure to say this part though, silver mirror on the surface of the test tube. That's for a positive test for an aldehyde, because as I said before, it will be the Ag+ is getting reduced. So overall test results, Fehling solution, the aldehydes will turn from deep blue to brick red, and ketones will remain deep blue. And for Torrance reagent, the aldehydes are, for a positive test, the aldehydes go from clear to silver mirror, whereas ketones, should I say ketones, not kittens, remain clear. So I was to do, let's see, positive. Testing with acidified potassium dichromate. When you have your alcohols, with different types of alcohols. Primary, secondary, and tertiary. This is just to sum up again. So primary alcohols, green precipitate. Secondary alcohol also has a green precipitate forming. You can write don't write PPT in your exam. That just means precipitate. In the mark schemes, you'll say PPT, but don't say PPT, say precipitate. But that's just what it means. And then tertiary, no visible reaction. It's important to say no visible reaction. And for testing for alkenes, we can test the solution to see if the alkene functional group is present. And the test is adding bromine water to the solution. And if an alkene is present, the solution will lose its orange color and become colorless. If an alkene isn't, what I mean by this here is that it's said that alkenes are decolorized bromine water. The key word that all you really need to say for this here is that the positive test for alkenes with bromine water is that the alkene will decolorize the bromine water, and that's the mark. That right there is a mark for positive test when an alkene is reactive with bromine water. And if an alkene isn't present, it will not decolorize and the solution will remain orange. I personally prefer saying it will cause a color change from orange. It'll cause the bromine water. Alkenes will cause the bromine water to undergo a color change from orange to colorless. Because I've always been taught saying what your initial color is to your final color, but you can just say that it decolorizes bromine water. But for me, safety-wise, I'll always say the positive result for an alkene under bromine water is that it undergoes a color change from orange to colorless. You can say orange-brown to colorless. How the test works? The test works because if an alkene is present, it undergoes an additional reaction with bromine, and this removes the bromine in the bromine water and forms a halogen alkene. So the color is lost. A quick note that bromine water is just bromine with a small amount of bromine dissolved in it. It's a very dilute bromine solution. That's hence the name water. It's not HBr. It's not that. That's hydrogen bromide or hydrobromic acid. It's not the same as bromine water. It's just Br2 together, but it's a very, very dilute solution. So it's hence the water part. And it's what colors the solution orange until it's reacted with an alkene. And yeah, alkanes can't have carbon-carbon bonds broken. So I'm going to show you the reaction here in case you forgot what it was. It's just an electric. Actually, you know what? You can do this, actually. Yeah. Pause the video now and then just draw the rest of this mechanism out. I've done this video before, so you should be able to do this. Alright, so first thing I'll do right here is that I'll actually do my partial charges. And then it's because you want to show that this is the double bond is very electron dense, and that's acting as a nucleophile, and this bromine here is acting as an electrophile. So it's always going from this double bond here where it's electron dense to this first bromine here that's partially positive, and this is partially negative. you do that, you form a carbocation intermediate. Why did I put a H here? My bad. When you have that here, you have this Br minus. That acts as a nucleophile. And that's it. That's all you need to do, and that's you get a mark for this reaction. So 1 mark here. Oh, I almost forgot to put this here. That's a mark that I forgot to put down, because that would have to break off first. So my bad. If I didn't do that in the previous video, my bad. I forgot that here. I don't even have that in my notes. But this is just something that I realized. When you do this enough times, you can just see where these things are. I haven't done my exams in a very, very long time now, so a bit rusty. But the point being, 1 mark here, 1 mark here. I don't think you get a mark for partial charges, but you may do. A mark for the carbocation being shown, a mark for this arrow here, and you get a mark for, you usually get a mark just for showing the structure overall, this intermediate here, but that'll be the 5 marks. The final product, you don't actually, or you should show your final product, but I've never actually technically seen you get a mark for your final product. It's just, but you should always write it down anyway. So, yeah, as I said before, alkenes, you can't break these carbon-carbon, because your alkenes can't have carbon-carbon single bonds broken. That's why this reaction here wouldn't happen with alkenes. You can't have electrophilic addition. You may be confused because I've just broken carbon-carbon single bonds, but that's carbon-carbon single bond. Carbon-carbon double bonds you can. Very electron dense. That's why it can happen. But when you have this, is very non-polar. This is a very non-polar bond. This here, well, that is technically because it's got the BRs here, but carbon-carbon single bonds are non-polar and wouldn't react. So testing for alkenes. They can become orange. And so when you add bromine water, so you add bromine water. And it either stays orange and that is no alkene present, or becomes colorless or decolorizes the bromine water. Oof. I can't write today, can I? And when it decolorizes bromine water, there is an alkene present. Testing for carboxylic acids. We can test to see if carboxylic acids are present in the solution. The test is firstly reacting the carboxylic acid with a sodium carbonate, and then the reaction of a carbonate ion should form. This is a neutralization reaction in acid and a base, because sodium carbonate is very basic. So the reaction of the carbonate ions should form a salt, which would be the sodium carboxylate, whichever carboxylic acid you have, CO2 and water. So we can test for the presence of CO2. So what you're doing in this reaction is you're proving the presence of a carboxylic acid by proving the presence of CO2 that's formed. So they might ask you to draw an apparatus for this, and it's a very simple test tube reaction. You have one test tube here, another test tube here, a bung, you have something to funnel your gas through, and this would be your carboxylic acid with your sodium carbonate. So you have a solution of your carboxylic acid with your sodium carbonate, or your carbonate. It doesn't actually have to be sodium carbonate, but it can be just a carbonate. And this will also be this gas gets funneled over to some lime water. This is just some CO2 bubbles in the lime water. Right, lime water. So lime water is a clear solution that turns cloudy if CO2 is present, meaning that we must pump the gases produced from the reaction between the sample and the carbonate into lime water. And if the lime water turns cloudy, carboxylic acid is present in the initial solution. And if lime water stays clear, carboxylic acid isn't present in the initial solution. All it is that what I'm trying to say is that you form CO2 from this reaction. This reaction here between the carboxylic acid and the carbonate forms your sodium carboxylate. It's a neutralization reaction. Your salt plus water and CO2. The all interested in is CO2. So when we form CO2, this CO2 will then be funneled over. It doesn't have to be pumped necessarily, but it's funneled in this little tube here, and this is funneled to the other side, which is this test tube that contains lime water. Lime water turns cloudy under the presence of CO2. So a positive test for CO2 being present is lime water turning cloudy. If the lime water turns cloudy, CO2 is present, and therefore we know that our original solution must have been a carboxylic acid, and that's how we test for the presence of a carboxylic acid. Hopefully this video was useful, and that is it.